All right, let's jump right in. Today, we are exploring one of the most mind-bending concepts in all of science, a theoretical shortcut through the very fabric of space and time itself. But first, to really appreciate the solution, we've got to understand the sheer scale of the problem. And that problem is that our universe is almost unimaginably vast. So let's take our closest major galactic neighbor, the Andromeda Galaxy. If we were to hop into one of our current spacecraft, traveling at a pretty brisk 28,000 kilometers per hour, it would still take us 94.5 billion years to get there. To put that in perspective, that's more than 6 times the current age of the entire universe. And the crazy part is, even if we could somehow travel at the ultimate cosmic speed limit, the speed of light, that journey would still take 2.5 million years. For a single human lifetime, travel between galaxies is it's impossible with our current methods. So that raises a huge question. Is there another way? What if there was a cheat code, a way to bypass all that distance, not by traveling through space, but by literally folding space itself to create a direct path? It's an idea you have almost certainly seen before. And here's the kicker. While a wormhole just hanging out near Saturn is, pure science fiction, the basic concept behind it, that's not. It's actually an idea that's rooted in some of the most profound and complex physics ever developed. So scientifically, a wormhole is known as an Einstein-Rosen bridge. It's a theoretical tunnel that connects two completely different, vastly distant points in space-time. To get our heads around how that could possibly work, let's use a super simple analogy. Okay, imagine for a second that our universe is just this two-dimensional sheet of paper. To get from point A to point B, while the shortest path is just to travel across the surface in a straight line. Simple enough. That's the long way. But what if we're not stuck traveling on the paper? What if we could bend this 2D space through a third dimension? All of a sudden, points A and B, which are still far apart on the surface of the paper, are now right next to each other in 3D space. And that is the big idea right there. A wormhole would basically be like punching a tunnel through that higher dimension, connecting two distant points in our 3D universe with a path that's ridiculously shorter than any normal route. So, where did this absolutely wild idea even come from? Well, for that, we have to go back to the work of one man, Albert Einstein. Back in 1915, Einstein gave us his theory of general relativity. And at its heart are these things called the field equations, basically a complex rulebook for the cosmos that describes how matter, energy, and the fabric of space-time all interact. It's his explanation for how gravity works. Now, the really fascinating thing about these incredibly complicated equations is that, well, they're a bit like a math problem from high school. You know how a simple quadratic equation can have more than one correct answer? Well, so can Einstein's field equations. They actually allow for different possible ways our universe could be shaped and how it could behave. And so when other physicists started to really dig in and solve these equations, they discovered that they predicted some of the most bizarre, most exotic objects you could possibly imagine, starting with one we now know for a fact is real. Just 1 year after Einstein published his theory, a guy named Carl Schwarzschild found a solution that described a region of space-time so warped by gravity that nothing, not even light, could escape. He had mathematically discovered the black hole a full century before we ever managed to actually take a picture of one. But then, in 1935, Einstein himself, working with another physicist named Nathan Rosen, found a different valid solution. This one didn't describe a trap, it described a tunnel, a bridge connecting two different points in space-time. This was the wormhole. But, a tunnel needs an entrance and an exit, so if a black hole is the entrance, what on earth could the exit be? The math pointed to an object that was the perfect mirror opposite of a black hole, a white hole. So where a black hole pulls everything in, a white hole would violently push everything out. Nothing could ever get into it, but anything inside could escape. It was the perfect theoretical exit for a wormhole. So the theory gives us this complete picture. You've got a black hole entrance, an Einstein-Rosen bridge for the tunnel, and a white hole exit. The math all checks out. But is any of it real? Well, this idea has been slowly building for over 100 years. It started with Einstein's equations, which led to Schwarzschild's black hole, then the Einstein-Rosen bridge, and finally, in 1957, the physicist John Wheeler gave it that super catchy name, wormhole. But there are some pretty big hurdles to get over.
Okay, problem number one. White holes seem to break a really fundamental law of physics, the second law of thermodynamics, which basically says that disorder in the universe always increases. A white hole would be like watching an egg unscramble itself. It just doesn't happen. On top of that, most of the math suggests that any wormhole that did form would be so unstable it would collapse on itself faster than light could even get through it. And yet, there are these little, tantalizing clues. In 2006, astronomers spotted a massive gamma ray burst, but there was no exploding star to explain it, which led a few to wonder, did we just see a white hole? And then in 2015, scientists actually built a magnetic wormhole in a lab, and they successfully tunneled a magnetic field from one spot to another. So even if cosmic wormholes for actual travel turn out to be impossible, that quest for a shortcut through space, it continues. And incredibly, Einstein's very own equations offer yet another, totally different possibility.
It's known as the Alcubierre drive, and yep, it's another valid solution to the field equations. The idea here is that a spacecraft could surf on a wave of spacetime. It would contract the space in front of it and expand the space behind it, letting it travel faster than light without actually breaking the laws of physics in its own little bubble of space. And what's just amazing is that all of these wild ideas, from black holes to wormholes to warp drives, they all come from the same set of equations written down over a century ago. It really reminds us, as Einstein himself said, that the mysterious is what drives all real discovery. And that leaves us with one final big question. Are all these theories just interesting quirks of mathematics, or are they a potential roadmap? Will we one day learn to actually master the very fabric of the universe itself?